Hello, everyone. Welcome to today's lecture. Today, we're going to continue talking about optimizations, and in particular, we're going to talk about two important optimizations. The first one is dead code elimination, and the other one is constant propagation. Okay? Did I say continue? I meant to say we're going to start talking about optimizations. Okay. So far, we've come quite a long way. We reviewed lectures and parsers at the beginning of the course. We then had a section of the course on intermediate representations where we talked about the different ways that we represent code inside of compilers, including ASDs, control flow graphs, SSA form, etc. We then talked about runtime environments. We talked about the linkage convention. We talked about the storage convention to understand how the code interacts with the hardware and the operating system, etc. Then we talked about intermediate code generation, and we talked about how we go from an ASD down to a control flow graph with 3-address code, and we saw how we can traverse the AST and how we can try and use local information as much as possible, and how certain things are supported by the semantic analysis. And we also saw how to generate code for things like classes and objects and dynamic dispatch, and how we use virtual tables to do all these things. We then started talking about the optimizer, and we started by talking about analysis. We saw some peephole optimizations first, and then we started talking about global data flow analysis, and we saw how we can analyze entire control flow graphs to find loops, and also to be able to do analyses such as reaching definitions, liveness analysis, and available expressions, etc. And we saw how all these analyses have this data flow framework in common that we can use, where we define local variables, and then we set up systems of equations to find the input and the output for each of the basic blocks, and then we solve that system of equations iteratively, and we pick a particular order to be able to converge in as few iterations as possible. So what we're going to move on today is to talk about optimizations. In particular, we're going to talk about machine-independent optimizations. And we're going to see how we apply these kinds of optimizations on control flow graphs, and what are the considerations that go into that. Before I start, any kind of questions about what we've covered so far, or the direction that we're going? All good? Okay, so let's start by talking about dead code elimination. So from the name, what do you think dead code elimination is?
Basically, the code that will not execute will just get eliminated.
Okay, dead code is code that will never execute, right? It's impossible to reach it, so it will never be executed. So we just remove it from the binary. So that's one kind of dead code. You're right. What are there other kinds of dead code? So code that we won't reach, or what else do you think is
maybe if we have a variable that has,
I'm sorry, I didn't hear you well.
Maybe if we have a variable that's like int x equal 8, and we have a loop for 8 times using x.
So that's, I think what you're referring to is redundant code, right? So there's dead code, there's redundant code. Redundant code is where we do the same thing many times, right? So there's a redundancy, and we're gonna have a whole lecture on redundancy elimination later on. But dead code is not code that executes redundantly, it's code that is useless, right? So useless code can either be code that I never reach, I never execute, or it could be code that I execute, but I never use. Right, it could be code that I execute, but I never use its result. So that's also referred to as dead code. So dead code elimination, or DCE for short, is an optimization that removes code that does not affect the result of a program. That's our definition of dead code. It's code that does not affect the result of the program, and this includes code that is unreachable or code that writes data that is never used. Okay? Now, what's the advantage of removing dead code? For the code that writes data that is never used, we save time, right? We get rid of that code, so we never execute it, we save time. But for code that is unreachable, we're never going to execute that, so what's the advantage of removing it?
Space, right?
Size of the code.
Right, we reduce space. We make the size of the code smaller, right? And even though we may not be too concerned about the size of the binary nowadays because we have a lot of space, a lot of memory, but the size of the code is also important because the code is fetched from memory, it sits in the instruction cache. So if I have smaller code, that means I'm more likely to find my code in the instruction cache. Okay, so then the advantages are we shrink the size of the code and we avoid executing useless instructions. All right, clear? Okay, now how can we do that code elimination? How can I remove code that is unreachable? If I have a control flow graph, how do I know that certain code is unreachable? Right, if there are no incoming branches into the control flow graph, that means the code is unreachable. How do I know if a code writes data that is never read? Correct. If I have SSA form, how can I find out? Right. If I have definition and the definition has no uses, right, that means that this code in the SSA graph, the data flow graph, if I have no uses for a definition, that means that definition is dead. Okay. So a naive algorithm, a naive or a trivial algorithm for dead code elimination is I can remove all blocks that don't have any incoming edges. I can remove all instructions that don't have any users. Okay, and then I can keep repeating this until the control flow graph stops changing. Why do I need to repeat this? Because if I remove a basic block that has no incoming edges, this might expose another basic block that previously had incoming edges and now does not have any incoming edges. Is that clear? Okay, so I remove blocks with no incoming edges, I remove instructions, no users, and also if I remove an instruction that doesn't have a user, the instruction that I removed might have been a user for a previous instruction. And now when I remove it, the previous instruction also no longer has a user. That's one example. Let's say I have this code right here, or this control flow graph right here. Okay, after I apply dead code elimination to this code, I iteratively remove blocks with no incoming edges and instructions, no users. What do I get?
A, C, D, E. We remove D. But now D doesn't have incoming edges.
So right, I'm going to remove B because it doesn't have incoming edges. And because of that, I can also remove D because D doesn't have any incoming edges. Okay, is there anything else I remove? So I'm left with ACE. Anything else I remove? Right, I can remove R2 equals 2, correct? Because R2 is not used anywhere. So I can remove R2 equals 2 as well. So here, this is an instruction that has no users. So this leaves me with the following control flow graph where the blocks B and D have been removed with all their instructions. And also the instruction R2 equals 2 has been removed because it does not have any users.
Doctor, in the example, shouldn't the phi function in E have R4 as well?
Shouldn't the phi function be, is your question, should the phi function be removed?
In the before, not after. Before we do the optimization.
The phi function is not removed because when we store, it means we're using R5, right?
No,
and then
I meant
R5 is using
R4.
R1 and R3.
That's from B. Shouldn't it be in E because we have an edge from B to E?
Are you
On the other
asking?
side. Yes.
Oh, you're saying that the phi function here should have also something that's coming in from B.
Yes.
Yes, you're right. So here, because I have 3 incoming edges, I'm supposed to have 3 input values right here. You're absolutely right. So here, this could happen if I had previously might have had a branch from somewhere that comes in here, and then I do some constant propagation, and this edge gets removed over here. So I need to kind of reanalyze the code to figure out what should have been the parameters of this phi function. So you're right. My code here is not precise. I should have a third parameter to my phi function here that is coming from somewhere over here. But that would get removed with the dead code elimination as well. But you're right.
Okay.
Okay, great. Let's do another example. So what about this example right here? If I apply dead code elimination to this code, what gets removed?
Okay, here it's a bit tricky. We need to remove C and E, but C has incoming edges from something that will also be, but from E, which will be
Right.
also removed because
That's right.
there's
So
no way to enter C but from E, and no way to enter E but from C.
yes, you're absolutely right. So here, clearly C and E are not reachable from the entry, right? So C and E are not reachable. However, if I, maybe before there was a branch coming in from here, and then I applied some optimization that realized that this branch never gets taken, so I remove the branch, and now C becomes unreachable. So, however, because C has another incoming edge from here, coming in from E, right? Even though C and E are unreachable, if I just go and look for basic blocks that have no incoming edges, I will never detect that C and E are unreachable. Okay, so that's one case. So here, blocks C and E are unreachable, but they are not eliminated because they all have incoming edges. Okay. Anything else that is dead code? In other words, code that doesn't affect the result of the program. However, it won't be removed.
R5? No, 5 is used, and R35. There's nothing.
So here R5 is here goes into the 5 for R3, and R3 is eventually used stored to memory. So it does affect R5 does affect the result of the program.
Maybe R4, because R4 is never
So let's
used
look at
in R3.
R4. So here R4, it uses R2 and R6, right? And then here I do R6 equals R4 plus R6, and then here I have R4 and R6. Over here I have R2. So here R4 uses R2 and R6, and R6 uses R4, right? And then R4 uses R6. But do R2, R4, and R6 affect the result of the program?
No.
They don't, right? For something to affect the result of the program, it means they need to somehow either get stored to memory so that after the program, so that they have some kind of impact, or maybe they are returned as a return value of a function, right? But if something is not used as a return value, it's not used in any of the branches, it's not used written to memory, it's just always the data just stays in the registers and never escapes from there. If it doesn't impact the control flow and it doesn't impact the memory, right, then it doesn't really have an impact on the program. So here, R2, R4, and R6, these lines that define R2, R4, and R6 don't impact the execution of the program. But can I remove them if I just look for instructions that don't have any users? No. Why not? Because I have a loop in between them, right? I have R4 is using R6 and R6 is using R4. So just like over here, I had a loop between E and C. I have E has a branch from C and C has a branch from E. That this loop between them prevented me from being able to detect that they're unreachable. Here, the dependence loop between R6 and R4 prevented me from being able to realize that the result doesn't affect the execution of the program. Okay? So R4, R6, R2, R4, R6 don't impact the program, but they're not eliminated. Okay, so clearly, this naive implementation of dead code elimination is not always effective. So we need to do something better. What do you think we should do to be able to remove these cases? So Okay, so we should do some kind of domination analysis, right? That makes sure that something does have is reachable from the entry. Okay, so maybe some kind of depth first search or something, right? Okay. What about the uses, the circular dependence of the uses? What can we do? Okay, so somebody is saying we can start from the store and then we can trace our way backwards until we find all the instructions that eventually impact that store. And yes, you're right, we can do that. So both of these, doing depth first search and starting from the store, are making a certain assumption. Okay, they are assuming when I do a depth first search, I'm assuming that everything is unreachable unless I can reach it. And when I do start from the store and make my way backwards, I'm assuming that instructions are dead until I can establish that they are alive. And this is called being optimistic. So the solution here is to be optimistic. What do I mean by see? We learn a lot of nice life lessons when we take compilers, right? You know, one of them is about the importance of optimism. The other one is separation of concern. Okay, so the previous algorithm that I presented is pessimistic. Why is it pessimistic? It's pessimistic because it assumes that all the blocks and the instructions are alive and then tries to prove that they are dead. It tries to assumes the block is alive, but it tries to find if it has an incoming edge. If it doesn't have an incoming edge, then it proves that it's dead and it eliminates it. Or it assumes the instruction is alive, but then it finds that it doesn't have any users. It proves that it's dead and it eliminates it. So in general, a pessimistic algorithm is an algorithm that assumes that a certain desirable property, in this case, that desirable property is for a code to be dead, right? It assumes that a certain desirable property does not hold and tries to prove that that property holds. And the problem with these pessimistic algorithms is that when there is codependence between establishing this property for different parts of the code, that codependence creates a kind of a circular dependence that prevents us from being able to prove that. So instead of using a pessimistic algorithm, the solution is to use an optimistic algorithm. And here, using an optimistic algorithm may yield better results. What do we mean by an optimistic algorithm? An optimistic algorithm will assume that everything is dead. It assumes that all the basic blocks are unreachable. It assumes that all the code is not used, and then it tries to prove that they are alive. And if it cannot prove that they are alive, that means they're dead, and it removes them. In general, right? In general, an optimistic algorithm assumes that a desired property holds, and then it tries to prove that it does not hold. Is that clear? Okay, so dead code elimination was a pessimistic algorithm, and we have an optimistic version of dead code elimination, and this is called aggressive dead code elimination, or ADCE. And aggressive dead code elimination is a variant of dead code elimination that is optimistic. It assumes that everything is dead and then tries to prove what is alive. So how does aggressive dead code elimination work? I'm going to kind of show you the pseudocode, and then I'll show you an example for it. So we're going to have first a helper function, and that helper function is called markLive. MarkLive basically marks an instruction as being alive. What we're going to do is we're going to have a live set, a work list that contains a set of all the live instructions. And every time we mark an instruction is alive, what we're going to do is, if it's not already in this live set, we're going to insert it into the live set. And we're also going to insert it into the work list so that we can process it later on. So we have a set of all the instructions that are live, and we also have a work list of instructions that here the work list contains instructions that we just discovered they are live, and we need to propagate that liveness information to the other instructions that are affected by this instruction. So whenever we mark an instruction as live, we check if it hasn't been live before, we insert it to the live set, and we append it to a work list. Now, having this mark live function, the aggressive dead code elimination works as follows. First, we're going to make an initial pass through all our code, and we're going to mark everything that is trivially live. Okay, what do I mean by trivially live? I mean everything that trivially impacts the execution. How do I do that? First, I initialize live set to the empty set, right? Because I'm assuming nothing is live. Then I will mark things as trivially live. I'm going to iterate through the basic blocks in depth first order. What that means is I will do a DFS from the entry block and mark every block, basic block that I reach as live. Sorry, I mark it as reachable. Excuse me, not live. I'll mark it as reachable. Okay, that means any block that is not reachable from the entry block is going to be automatically assumed as dead. Okay, so I mark every basic block as reachable, and then when I find a reachable basic block, I'm going to iterate through every instruction in that basic block. I'm going to check, is that instruction trivially live? What do I mean by trivially live? There are certain instructions that we consider trivially live. A store instruction is trivially live because a store instruction obviously impacts the outcome of a program. A return instruction, so if I have an instruction that returns from a function, that's trivially live because it impacts it. You know, it's returning data to our user, and we assume that our user will use that data. A branch instruction, for example, is trivially live because it's part of the control flow. So if an instruction is trivially live, we're going to mark it as live. We're also going to find instructions that are trivially dead. An instruction is trivially dead if it has no users. And in this case, we're going to remove these instructions from the basic block. So this is how we go through and we initialize everything where we know for sure that it is live. Now here, when we visited these trivially live instructions and marked them as live, what we've done is we've added them to a work list. Once we add them to the work list, the next step is to start going through that work list, removing instructions, and then propagating the liveness information to the instructions that are effective. So here we go through the work list and we find new live instructions. So while the work list is not empty, we're going to get an instruction from the work list. That's going to be instruction I. And then we're going to check if the basic block containing that instruction is reachable, because I could have an instruction that is not reachable, and it's in a basic block that is not reachable, but somehow, for example, if you have a phi function, like we pointed out earlier, but the phi function is coming from an instruction that is, the phi function, it's coming from a basic block that's not reachable, right? I don't want to mark the instruction inside of that basic block as live. So if the basic block containing the instruction I is reachable, then what we do is we go through all the operands of the instruction I. So if I uses different operands, we go through these operands of instruction I, and if the operand of instruction I comes from an instruction, because the operand could be constant, or it could be defined by another instruction. If the operand comes from another instruction, then we will mark that operand as live. Is this clear? So we're going to get an instruction. We're going to make sure that instruction is in a basic block that's reachable. And if that instruction is reachable, then we go through all the variables that instruction uses. If these variables are defined by other instructions, we're going to add those instructions to the working set, to the work list by marking them as live. Now, once we're done doing this, we keep iterating until the work list is empty. Once the work list is empty, it means we've propagated this liveness information to all the other instructions. Now what we can do is we can delete all the instructions that are not in the live set. So we can go through all the basic blocks. If the basic block is reachable, then for every instruction in the basic block, if that instruction is not in the live set, we're going to erase that instruction from the basic block. Okay, so this is the pseudocode for aggressive dead code elimination. And if you didn't follow too much, let me do a simple example. So let's go back to this example. We said the first step of dead code elimination is to iterate through every instruction in all the basic blocks in depth first order. And for each instruction in that basic block, if it's trivially live, we're going to mark it as live. Okay, so here if I iterate through this control flow graph in depth first order, what basic blocks do I reach? What basic blocks do I not reach? So A, B, D, and F are going to be reached, right? And then the C and E are not going to be reached. Okay? So when I iterate through these, so I'm going to iterate through A, B, D, and F. I will not visit C and E. Now, as I iterate through A, B, D, and F, I'm going to mark all trivially live instructions as live. Which instructions in A, B, D, and F are trivially live? The store instruction, right? Anything other than the store instruction? No, just the store instruction. Okay? So what I'm going to do is I'm going to mark the store instruction as trivially live. And remember, when I mark an instruction as trivially live, I do two things. I insert it into a live set. Basically, that tracks if something is live, and I add it to a work list. So if I go back here, what I'm going to do is I'm going to mark the store as trivially live here. I'm just going to indicate that with this orange color, and I'm also going to add the store instruction to a work list. Clear? Okay. Now that I've finished initializing all trivially live instructions, the next step is to keep iterating over the work list, remove instructions from the work list, go to all their operands, right? And if the operands come from instructions, mark those instructions as live. So here, if I come back here, first I remove the store from the work list, right? So I'm going to remove the store from the work list. The store, I go through the operands. What operands does the store have? It has R3. So then what I will do is I will go to the operands of R. I'm going to mark R3 as live. And then I'm going to go through the operands of R3. In this case, they're R1 and R5. And I'm going to add the R instruction that defines R1 and the instruction that defines R5 to the work list. So now I've added R1 equals 1 and R5 equals 5 to the work list. Okay. Next, I'm going to remove R1 from the work list, go through its operands. Here, its operands are all constant, so I don't add anything to the work list. Same thing for R5. I remove R5 from the work list. I go through its operands. Here, the operand is 5. It's a constant, so there's nothing left to add to the work list. So I keep iterating. I remove R1, I remove R5. I mark them as live until I am done. So now that I am done, anything that I haven't visited and marked as live, that is going to be assumed to be dead. So here, C and E were not reached by the DFS, so they are going to be dead. And R2, R4, and R6 are never reached as I was iterating over the instructions in the work list, so they are also going to be dead. Is this clear? Okay. Then the final step is to iterate over all the basic blocks, and if the basic block is reachable, go through every instruction, and if it's not live, remove it. That's fairly straightforward. So basically, I'm going to go through all these basic blocks, and here R2, R4, and R6 are never marked as live, and also R7 and the store are never marked as live. So I'm going to iterate through them, and I'm going to remove them from the work list, and that leaves me with this code right here. So here, aggressive dead code elimination leaves us with, of course, also C and E are going to be removed. Okay, so this is how, by being optimistic, we were able to get rid of these instructions that dead code elimination was not able to get rid of. Is this clear? Any questions? Okay, great. So now let's move on to the next optimization, or two optimizations, which are constant propagation and constant folding. Okay, so what do you think constant propagation, constant folding are? I think we talked about them before. What's constant propagation? So constant propagation is where if I have a constant, I start plugging it into wherever it is used. Okay. So constant propagation is an optimization that substitutes the values of known constants at compile time. What about constant folding? Constant folding is used with constant propagation. And constant folding is if I have an expression where all the operands of that expression are constants, I can evaluate that expression at compile time. Okay, is that clear? What are the advantages of constant propagation, constant folding? I save time, right? If something is constant and I can calculate at compile time, I don't have to calculate it at runtime. So I perform fewer computations at execution time. What's another advantage of propagating constants? You make the code smaller, yes. Fewer instructions, you make the code smaller. What else?
The symbol table.
I can't hear you online.
The symbol table, the place where we place the variable name and its value.
So the symbol table we use while we're doing the analysis is going to become smaller. That's beneficial, right? But the symbol table in the final code is not going to be affected because usually we don't have symbols for the variables. Okay, but what's another benefit of propagating constants? Think about what we discussed earlier in this class. How can I find when I do that code elimination? How do I find out that a branch that a basic block is unreachable? By knowing that a certain branch has a constant condition. How do I know that the condition of the branch is constant? By doing constant propagation and constant folding. So doing constant propagation, constant folding can expose opportunities for dead code elimination by finding the branches whose conditions are constant. Okay? And this is why we apply these optimizations over and over. So let's do an example. Let's say I have this code right here. X equals 1. If x is greater than 0, y equals 1, else y equals 2, z equals y plus 1, and then store z. Okay? If I apply constant propagation to this code, what happens? So remember, constant propagation will take a constant and we'll plug in the constant value wherever that constant is. So here I know x equals 1. I know x is a constant. So what can I do? I can substitute wherever all references to x with 1. So here, instead of having x greater than 0, I can apply constant propagation. Now I have 1 greater than 0. Okay, so that's what constant propagation does. Now that I've done constant propagation, what can I do? I can do constant folding. What does constant folding do? It finds all expressions that have constant operands and it evaluates them at compile time. Okay, in this case, what expression has constant operand? Right, 1 greater than 0. So here 1 greater than 0, right, is a constant. So I can evaluate it and it becomes true. Okay, now here I'm showing code, but think of the basic block. Here, when I have a branch and that branch contains a constant as a condition, it becomes a jump, right? It becomes like an unconditional branch. Okay, so now after I do this, okay, what can I do? I can apply dead code elimination. What would dead code elimination do? Right, so dead code elimination will remove the branch. Here, I no longer have a branch to y equals 2 because the if condition always goes to y equals 1. So dead code elimination is going to get rid of, well, first of all, it's going to get rid of x equals 1 because x is no longer used anywhere. And it also gets rid of y equals 2 because the branch into y equals 2 is gone. So I'm left with the following after I apply dead code elimination. By the way, here I only need to apply dead code elimination. I did not need to apply aggressive dead code elimination. Okay, and as a matter of fact, I talked about dead code elimination and I said it's pessimistic compared to aggressive dead code elimination. So aggressive dead code elimination is better, but aggressive dead code elimination is better at exposing more opportunities for dead code elimination. But is dead code elimination better than aggressive dead code elimination at anything? Right, dead code elimination is simpler than aggressive dead code elimination. So in the compiler, I actually have both. I have dead code elimination and I have aggressive dead code elimination. The reason I have both is because DCE is much faster to run than ADCE. So usually when I'm doing an optimization sequence like this, I will do DCE over and over because it's cheaper. And then every so often, I will do aggressive dead code elimination, which is going to be a little more expensive and take more time. Is that clear? Okay, so here I only need to do dead code elimination. Okay, now that I've done dead code elimination, what can I apply again? I can apply constant propagation again. If I apply constant propagation here, what happens?
So that بتصير دايرة 2.
Right, I plug in 1 wherever there's a y. So I can plug in 1 right here. Now it becomes y equals 1, z equals 1 plus 1, store z. Okay, now what can I apply to get rid of this 1 plus 1? I can apply constant folding again. And when I apply constant folding, I get z equals 2. And then after that, this y equals 1 is no longer being used. So how can I get rid of it? I can apply DCE again, and I'm left with z equals 2, store z. Okay, so here you can see how constant propagation, constant folding, dead code elimination work together. And remember before how I told you about separation of concerns and how we want to separate the optimizations so we can apply them in different orders and apply them over and over again. This is a perfect example of how applying multiple optimizations over and over again is useful. And here we're going to apply the optimizations iteratively until we change. No, we don't change. So constant propagation, constant folding, and dead code elimination are very cheap. So we can apply them. We can apply the 3 of them over and over and over and over until the code stops changing. Once the code stops changing, we know that there are no more opportunities for these 3 optimizations. Is this clear? So somebody's saying if this was return z, or even if it was store z, yes, I can plug in 2 here and become store 2. It depends on the IR, right? Depends on the IR. If the IR supports that you return a constant or you store a constant, then yes, you can do it. Okay. So here, yeah, I can run constant propagation again, it becomes store 2, and then I can run dead code elimination again, I get rid of the z equals 2, etc. Okay, great. Let's do another example. So let's say we have this example right here. I have x equals 1, and then I have while some condition, I do y equals x, and then I have some more code, and then I do x equals y. Okay. Now I'm showing you here the code instead of the control flow graph. But when I convert this into SSA, I'm going to do something a little unconventional here. So here, if I convert this into SSA, this is going to be x1, this is going to be x3, and I'm going to have a phi function here, x2 equals phi, x1, x3, right? So think of the control flow graph, but I don't want to draw a whole control flow graph because I'm going to be changing it a lot. So here I have x1 coming in. Here I have x2 equals phi, x1, x3, and then here I'm using x2, and then over here I have x3 equals y, and that x3 comes back over here. Okay? All right, now let's say I want to apply constant propagation. What do I do? Well, first of all, before I apply constant propagation, so here x equals 1, y equals x, x equals y. So it's clear to everyone that x and y are always 1. Correct? Does everybody see that? Anybody disagrees? Okay, so now when I want to apply constant propagation, and right, if I apply constant propagation, what I do is I'll plug in x1 equals 1 here, but then I have x2 equals phi of a constant 1 and then x3, which I don't know, right? So I cannot establish that x2 is 1 because I don't know x3. I need to know that x3 is 1. And because I cannot establish that x2 is 1, I cannot establish that y is 1. And because I cannot establish that y is 1, I cannot establish that x3 is 1. Okay, so I cannot establish that x2 is 1 because I don't know what x3 is. I cannot establish x3 is 1 because I don't know what y is, and I cannot establish that y is 1 because I don't know what x2 is. Okay, so what's the problem here? Right, the problem is I wasn't able to figure out that x2, y, and x1, x2, x3, and y are all 1 because I have some kind of circular dependence between them. Okay? So what's the solution to this problem? How can I solve this problem? Hint, we've seen this before today. Right, so before I had a circular dependence, right? And how did I, with the dead code? Right, to solve this problem, I need to be optimistic, right? So far, what I tried to do here is pessimistic. How's it pessimistic? Right, this algorithm has been pessimistic because I'm assuming that everything is not constant, and I am trying to prove that it is constant. Okay, and that's why when I come here, I have the 1 and I have x3, which I don't know yet, right? I'm assuming that x3 is not constant, and I'm not able to figure out that I have a constant. So this is a pessimistic algorithm. Instead, what we can do is we can use an optimistic algorithm. What would be the equivalent of optimism in this case? Right. The optimism would be to assume that everything is constant and then try to prove that they are not constant. We don't just assume that everything is constant. We assume that everything is whatever constant we would like them to be. Okay? And I'll elaborate on that. So the solution here is to use an optimistic algorithm. The pessimistic algorithm assumes that no variables are constant by default and tries to prove that they are. An optimistic algorithm is going to assume that all variables are constant by default and then tries to prove that they are not. Okay? Now, in order for us to be able to track this constant, we need to define something which is a lattice. So what is a lattice? A lattice is a partially ordered set where every pair of elements in the set has a unique least upper bound. We call this the join, and it has a unique greatest lower bound. We call this the meet. Okay? So it's a partial order. People here know what a partial order is, but there's a special kind of partial order where there's always a unique, for every pair, there's always a unique least upper bound, a unique greatest lower bound. A bounded lattice is a lattice that has a greatest element and it has a least element, and we refer to these greatest element, least element as top and as bottom. And why are lattices useful? Lattices are useful because they help us track constants when we are doing optimistic constant propagation. Okay, let me do an example. So this is an example of a constant lattice. Okay, it's a partial order. Every item in this lattice, every item in the set is a constant. Okay, now the constants with respect to each other are unordered, right? 1 is not more constant than 2. 2 is not more constant than 5. They're all equally constant. No constant is better or worse than another constant. However, these constants have a upper bound and a lower bound, and in this case, this upper bound and the lower bound are also they all meet at the bottom and join at the top. Am I using that terminology correctly? Yes. Okay, so they're all joined at the top and they all meet at the bottom. Okay, and here the top is something that is more constant than any of these other constants in the lattice. What is more constant than a specific constant? It is the idea that something can be any constant we want it to be. Okay, that's what top means. And then the bottom means that something is, what is less constant than a specific constant? It's something that is not constant. Okay, so top intuitively means that something may be any constant we want it to be. And here, top is the greatest in our partial order, and any constant Ci. So here, C minus 1 refers to the constant minus 1. C0 refers to constant 0. Ck refers to the constant k. So here, any Ci is less than top for any I. Bottom, intuitively here, means that something is not constant. So if something has the value bottom, that means it's not constant. Okay, and bottom is going to be less than any other constant. Okay, and there is no ordering between constants, right? So between two constants Ci and Cj, there's no ordering between them. So I can't say that one constant is more or less constant than another constant. Okay. Okay. So the x meet y is the greatest value that is less than or equal to both x and y. What does that mean? It means that if I have two values, the meet of them is the value that is less than or equal to these two values. So here, if top meets a constant Ci, if I have a top and I have a constant Ci, and I run a meet operation on them, then top and C negative k meet at negative k. So negative k here is the value that is the greatest value that is less than or equal to both top and negative k. What about bottom meets Ci? So bottom meets C negative k is going to be bottom, right? The bottom is the value that is less than or equal to a negative k. Ci meets Ci. Where does Ci meet itself? Ci meets Ci at Ci. The value that is less than or equal to both Ci and Ci is Ci. What about Ci and Cj? If I have C minus 1 and C1, where do they meet? They meet at bottom. Okay, so this is, again, a meet means it's the greatest value that is less than or equal to both Ci and Cj. So two constants, they meet at the bottom if I does not equal to j. Okay, how is this useful? It's useful because when we have a phi function has multiple operands, and these operands somehow meet at the phi function. So when something that is a specific constant meets something that can be any constant, the outcome of that is going to be the specific constant. When something that is a specific constant meets something that is not a constant, the outcome of that is going to be not a constant. When two different constants meet at a phi function, then the result is going to be obviously not constant. And then when the same constant meet, the result will be that constant. And when two different constants meet, the result will be not a constant. Okay. So how do we use this to run an optimistic constant propagation? Let's take a look. So here we come back to our example. And here in our example, what we're going to do is we're going to start by assuming that all of the variables are top. Remember, what does top mean? Top means that something can be any constant we want it to be. All right? So I'm going to start by assuming that all my variables are constant. So I'm going to assume that x1, x2, y, and x3 are all constant. Not just constant. We're going to assume that they are going to be any constant we would like them to be, whatever is convenient for us. Okay? All right, now what we will do is we are going to iterate over the code over and over. We're going to keep iterating over the code, okay, until it stops changing. And every time we get to a phi function, we're going to execute the meet operation in our lattice. Okay, so we'll start with x1. When we go to x1 equals 1, we learn that x1 is what? X1 is not top. What is x1? X1 is the constant one. We're going to denote that as C1. Okay, great. Now we go to x2. X2 is phi of x1, x3. Okay, so what should x2 be? Well, x1 is constant 1, C1, and x2 is top. Right? So then x3 is top. So then x2 is going to be the meet of C1 and top. Where do C1 and top meet? At C1. So here, what we do is we set x2 to C1. So x2 is the meet of x1 and x3. The intuition here is that we assume that x3 is going to be any constant we would like it to be. So when any constant we would like it to be meets the constant 1, the result is going to be the constant 1, right? This is where the optimism helps us. Okay, great. Now we go to y equals x2. So when we go to y equals x2, okay, x2 is what? It's C1. So then y is going to be what? It's going to be C1, the constant 1. Okay. Then we go to x3 equals y. Well, we know that y is C1. So then x3 is going to be what? It's going to be C1. Okay. And now we keep iterating. So we can be smart about this, and whenever we modify something, we enqueue all its uses, or we can just iterate over the whole thing. But you notice if I here after I do x3 equals y, I've changed x3 used to be top, now it's C1, so I've changed x3. So I go back and I go reprocess whatever uses x3. So here x2 uses x3. So now if I come back and I process x2 equals phi, x1, x3. This time, what do I have? I have x1 is C1 and x3 is C1. So where do C1 and C1 meet? At C1. So now if I do C1 meets C1, I get C1, and x2 here is already C1. Okay. So if I keep iterating, there are no more changes, and by doing this, I've established that x1, x2, y, and x3 are all the constant C1. Is this clear? So this here is an example of how, by being optimistic, assuming that everything is constant until I can prove that it's not constant, we were able to detect that all these variables x1, x2, y, and x3 are C1 in a situation where just doing the regular naive constant propagation was not able to do that. Any questions? Okay, let's do another example. Let's say we have this example right here. Here I have x1 equals 1, x2 equals phi, x1, x4. If x2 is less than 0, x3 equals minus 2. And then we have x4 equals 5, phi of x2 and x3. So here in this code, let's just kind of intuitively look at it. So x1 is 1. So the first iteration, x2 is going to be 1. Okay. So here, 1 is not going to be less than 0, correct? So we're never going to go into this if statement and make x3 negative 2. Okay, so it's clear from this example that x1 and x2 and x4 are always going to be 1. Okay, but let's see if our optimistic constant propagation can track that, can discover that. Okay, so we're going to, as before, we're going to initialize x1, x2, x3, and x4 all to top. We're assuming that everything is constant. Not just that, we assume that everything is whatever constant we would like it to be. Okay. Now we process x1 equals 1. We learn that x1 is what? C1. Okay. Then we go here. x2 is phi of x1, x4. So I do x1 meets x4. x1 is C1. x4 is top. So C1 meets top where? At C1. So here x2 is going to become C1. Okay, then I'm going to go to x3 equals negative 2. When I do x3 equals negative 2, what is x3 going to be? C negative 2. So I do x3 equals C negative 2. Great. Now I come down here, I do x4 equals phi of x2, x3. What is x2? Well, x2 is C1. What is x3? It's C negative 2. Where do C1 and C negative 2 meet? What does C1 meet C negative 2? At bottom. So here, x4 is going to be bottom. It's not constant, right? Because here I see that I can get a 1 from here, or I can get a minus 2 from here. So x4 is bottom. So now after I process x4, I go and I process the users of x4. So here x2 is a user of x4. So here, x1 meets x4 where? Well, x1 is C1 and x4 is bottom. So where does C1 meet bottom? At the bottom, right? So here, x2 is going to be bottom, become bottom. And when x2 becomes, so x2 becomes bottom. And then I iterate, and then there are no more changes. So as you can see, even though intuitively, when we look at this code, we know that x2 and x4 are always going to be 1 because I'm never going to come into this if statement, right? I was not able to detect this even by being optimistic. And no matter how much I repeat constant propagation, constant folding, dead code elimination separately, I cannot detect that x2 and x4 are 1, even if I am being optimistic. Is this clear? What's the problem? Why am I unable to detect that x2 and x4 are constant by repeatedly applying constant propagation, constant folding, dead code elimination? Right. So when I'm running constant propagation, the constant propagation is unable to tell that x3 will never be reached. Why is it unable to tell that? Because it's constant propagation. It's not dead code elimination, right? Constant propagation doesn't go and figure out which branches can be executed, which branches cannot be executed, right? All it does, it treats all code as if it's reachable and just analyzes its constant properties. Okay. What about dead code elimination? Why was dead code elimination not able to eliminate this branch? Right, because dead code elimination doesn't know that x2 is a constant. Okay, so here the problem is something we've been kind of very happy with since the beginning of the course, which is separation of concerns. Okay, so far we've been very happy with separation of concerns because we're saying that by doing constant propagation, constant folding, dead code elimination separately, we can implement each one separately. They're very simple to implement. They're very easy to implement. They run very efficiently. They run very quickly. I can repeat them over and over until the code stops changing. But the separation of concerns actually came back and bit me here, right? Because here, to be able to know that x2 and x4 are both 1, I need to be able to run constant propagation and dead code elimination together at the same time. And no matter how much I run constant propagation and dead code elimination separately, I will not be able to figure out that x2 and x4 are constant, are 1, and that this branch is dead. Is this clear? Okay, so separation of concerns is beneficial when the separated operations can be performed independently while achieving the same objective. So when separation of concerns makes things simpler without making me lose information, without preventing me from being able to achieve the same objective, then separation of concerns is good. However, in this particular scenario, the separation of constant propagation, constant folding, and dead code elimination into 3 independent optimizations caused us to not be able to capture certain information in certain scenarios. Is this clear? So what is the solution in this case? The solution is that we need to have, it's still good to have CP, CF, and DCE in our code because they're cheap, they're simple, we implement them over and over. But we occasionally need to have another optimization where we combine constant propagation, constant folding, and dead code elimination into one optimization that is going to have the full view of the constants and the dead code inside of our code to be able to tackle examples like the one that I just presented. So it's beneficial to have an optimization that combines these 3 into a single optimization. And this optimization is called sparse conditional constant propagation. And we will be covering this optimization next time. Okay. Any questions? So that's all I have for today. Next time, we're going to delve into sparse conditional constant propagation, which is an optimization that gets rid of the separation of concerns and combines constant propagation and depth elimination together in one monolithic optimization. It's going to be an expensive optimization, so we don't always apply it, right? But whenever CPCF and DCE stop changing the code, that's usually an indication that it's a good time to try sparse conditional constant propagation and see if there are opportunities that it can uncover that these three cannot. Any final questions? Okay, if there are no questions, then that's all for today, and I will see you next time.